Professor Heng-Yu Chen giving the talk. Heng-Yu did his PhD at Cambridge in 2007. As far as I could tell, he made quite a splash in terms of publications. Then he went on to Wisconsin for 4 years. I don't know why 4 years, but
they love me, I love them.
They loved you up, produced papers. And I think it's at that time he probably already applied, but he went on to Cincinnati, somehow Cincinnati and Kentucky, as far as I can tell. Well, actually, he put it himself on Department's web. And so in fall 2011, but already returned to Taiwan in 2012. And last year he received the Young Scientist Award from NCTS, and doing pretty well. I think he's an unusual stringer, but more diverse than just normal strings. So today he's going to tell us about surface defects and dualities in supersymmetric gauge theory. So Henry, the floor is yours.
Okay. So thank you very much, George, for the invitation, and it's my great pleasure to be entertaining you guys this afternoon. So today I would like to talk about a class of interesting non-local observables in supersymmetric gauge theory. In fact, you can find them in the normal gauge theory as well, and their connection with the recent progress in obtaining or computing exact results in the supersymmetric gauge theory. Okay, so surface defect, that's the talk today. And so what are they? Well, so they are the generic name referred to a codimension 2 non-local observable in 4-dimensional gauge theory. So codimension 2 here simply means that in the transverse to this particular object we are looking at, there are 2 orthogonal dimensions. So what are they? Well, so probably the best known example actually arises from your familiar abelian Higgs model, which you are dealing with a superconductor when you write down an effective field theory description for the symmetry breaking the superconductor. So this is our abelian Higgs model. So we are dealing with a U1 gauge group, and so we have a Cooper pair that usually is going to be given by some complex scalars, and we also turn on the electric charges, and also basically we have something called Fi parameter to arrange people, or basically just describe the size of condensate for your Cooper pair. So the aim here is really trying to find a static solution which gives rise to a minimum of the path integral. And what do we do? Well, so we write down a Hamiltonian, and we try to look for a saddle point.
Can I slow you down?
Yeah.
What does codimension really mean?
That means, for example, in 4 dimension, well, for example, like a monopole is a line in 4 dimension, it's a wall line. So that would be codimension 3. Okay. And the codimension 2, that means, so it's a 1 plus 1 dimension in 4D, so there are 2 dimension transfers to it. And in 3 dimension, if you have a line object, then that will be a codimension 2 also. It's just a name.
If I don't know, it means that except your string or, I don't know, high-powered field theorist audience, why is it called codimension?
Oh, it's what completes the entire space-time. So, no, it's not high-powered, it's just added to it.
It's just strategic, but
yeah.
I still don't understand it. What is, besides a somewhat fancy name, what is in that name? Why can I just call it? It's.
Oh, okay. So it's a 1 plus 1 dimensional observable. It's just that this analysis can be easily generalized to other dimensions as well. Okay. So you can actually consider about 3 dimensions. That it can be the line. Then it can be a magnetic monopole line in the 3 dimension. Okay. And it could be a 5 dimension. Then that would be a 3-dimensional defect. Again, codimension 2. But regardless, so we are trying to find right. So we were trying to find the minimum of the saddle point, the saddle point from the Hamiltonian, And they can come from basically this completing of a square trick. Now you can just look at Hamiltonian and find out, well, yeah, you can actually complete them. And so since all the squares are positive definite, and you can only have a minimum if those fields like F and Q actually satisfy the following equations. And so this solution, basically, as George was trying to ask, is actually spending 1 plus 1 dimension over the time and over the x3. So it's actually static in space. And so they are transverse 2 dimension to it, like x1 and x2. So, and basically, whatever minimum you are obtaining from this Hamiltonian, that has to satisfy those equations of motion. And those vortex equations, when you basically, well, plug in a solution into a Hamiltonian, then you will see that basically your minimum tension per unit length is actually given by the first, basically, the field strengths are integrated over the transverse plane to this 1 plus 1 dimension. And that's actually worked out to be a, well, we say 2 pi times the Fi parameter and times the integer k. So,
excuse me, may I still ask,
okay, sure, go.
the Billion-Higgs model is the superconductor, so vortex is not always a solution, so this is a special solution.
Right, those are basically describing a flux tube in a superconductor.
Right, so
yeah,
type 2 superconductor.
Type 2 superconductor.
But in this framework, what about the vortex thickness? Or
right, so the vortex thickness is going to be given by the inverse of the, basically it's going to be 1 over E times this condensate size.
Just that? I thought it would be, it would not depend on further material detail.
Well, so this will be the parameter you will feed in for your material details. Yeah.
I was just curious because I thought.
Yeah, it's fine. Yeah, it's actually good to ask. Just keep interrupt and keep asking questions. Okay.
No, I thought this would be more idealized. So, but if I think in terms of a genuine BCS type or whatever type 2 superconductor that has vortices.
Right.
I'm not in that field either, so I'm just saying that the vortex thickness, I would have imagined that it does depend on some other material property, but it doesn't appear here at all.
Well, this is the material parameter.
It is, but I thought, the vortex is letting the magnetic field go through, as this ansatz shows. But I would have thought that, for instance, it would depend on temperature. Right?
It would depend on
and it would depend on temperature, but also depends on, is the dependence on material only through the condensate strength itself? It's a little bit amusing to me. You're saying a vortex solution would not provide any extra dimensional parameter. Is that a simplification or?
Well, it's a simplification. It's basically described as symmetric breaking. But you can also imagine that, well, what's a flux tube? Well, it's basically confine your U1, well, your electromagnetic fluxes inside those, the thickness, which is basically only given by, only given by the 1 over the
in this case, there's no extra parameter.
There's no extra, I mean, I'm not, yeah, that's right. So we are now having like additional like temperature parameter and so on and so forth. But of course, I mean, those information can be encoded in those coupling E here as well. And then in fact, if it's not particular those ratio, you wouldn't have all this completing on square. You don't have a vortex solution, and you're off critical if you want. Yeah, so I think they are additional, and in fact there could be higher correction terms as well. But okay, so how do we really understand, well, this integer? I guess I will have to be very slow today. So basically, asymptotically, if you look at the spatial infinity, well, so we basically go to a vacuum of the theory, and that's where the symmetry is actually precisely, well, the U1 electromagnetic gauge symmetry is precisely broken. And that's the point where the complex scalar field actually pick up this condensate value. And so if we look at the integral we have just now, right, we can turn that into an elementary, basically that's a surface integral, and we can turn that into a line integral. And that just depends on basically the loop going around the infinities, the spatial infinity. And now go around that circle, but we also know that we are describing actually a vortex. This gauge field is describing a vortex solution that from the covariant derivative that we defined the vortex equation just now, that we can relate the gauge field to the scalar field. And that's basically just telling you, well, the winding number. So basically, that's this scalar field Q is actually mapping a spatial infinity, this S1, onto your vacuum manifold, which is actually described by basically original gauge group, so to speak. And this kind of winding, just like, it's basically, this kind of command is characterized by the topological winding number pi1. And that naturally gives you an integer telling you how one circle winds around another circle. But if we also think about, well, this is a contour integral, this is in a loop. Now, if you want to have a non-zero value, then it has to have some singularity, it has to have some poles. And those poles are precisely located where the vortex centers actually are, where you pin your flux tube, so to speak. And so those solutions, well, the explicit solution to vortices are really kind of, well, they're gauge dependent. So if you look at a singular gauge solution, that near the actual position of vortices, that basically the gauge field actually developed a singularity. Well, I mean, so this is actually the radial, this is the kind of angular profile. So if we write this transverse direction in a polar coordinate. So if you look at this, it actually goes like 1 over rho, in fact. So, and this is actually probably the most familiar example of the surface defect, the 1 plus 1 dimension. So we call it surface. And they are really specified by different kind of singularities one can obtain in the gauge field when you approach the position of those defects. Okay, so I hope this is clear. So, and like when we are studying, instant tone in the QCD, that we usually begin with the lowest rank, we begin at SU2 instant tone, and we can embed them into a higher rank gauge group by tuck it into the top left corner and leave everything else invariant. The same goes with those vortices, that we can actually embed it, this U1 gauge group, or the solution living this vortex solution living this U1, into the higher rank gauge group by tucking to one of the top left corner or something. So, and also that right now I only look at the bosonic degree of freedom, but we can also couple to the theory to a fermion. And if those fermions also transform under the appropriate representation, in fact, the same representation under the gauge group as your for example, Cooper pair, then you can have a possibility of supersymmetry. And this naturally, and then in fact you have a lot more control, like on the power of supersymmetry. So this allows us to really look at different kinds of vortices, or even more generally, more generalization of the surface operator inside the supersymmetric 4-dimensional supersymmetric case series.
Can I still ask what you mean by
Sure.
surface?
1 plus 1, the surface.
Where is it located? Just by defining
Right,
the
the define
0?
is equal the 2 complex coordinate in 4D, right? You can have x1, x2 equal to z, and so it's at the origin of the 1-2 plane, pin over there, but it spanned in the entire x3 and the time direction. So if you're in the Euclidean signature, then you are in the surface. Okay. So good. So any more questions before I go on? Of course, that will be coming. Let's see. So right. So the playground will be studying those surface defects, or the 4-dimensional n equals to UNC SQCD. It's basically a supersymmetric cousin of the QCD. But now we have additional NF fundamental flavors transformed the fundamental representation of the gauge group. And we have a gauge coupling for this gauge group. And in addition, we'll also turn on the FI parameter. So in this theory, if you actually look at Lagrangian, there are different branches of vacuum. Some vacuum actually preserve your electromagnetism. They are known as a Coulomb branch vacuum. But there are some vacuum which actually your gauge symmetry is actually completely broken, and they are usually called the Higgs branch vacuum. And for the lesson we learned about the U1 basically superconductor, the natural place to actually look at those vortices are really the Higgs branch. And so in terms of the expectation value of those fields in the gauge, in this gauge theory, the Higgs branch is really given by where this scalar field, which transforms in an adjoint representation of the UNC, or they are part of the so-called the equals to vector multiplet. That is actually set to 0. Because if it's not 0, then it's actually parameterized by the Coulomb branch. But also, now you have those additional kind of generalized version of the Cooper pair. Now actually take a non-trivial value that depends on the condensate. And in fact, a better way to even see is that those Coulomb branches are actually generally lifted by the presence of the Fi parameters. So you can't basically have a vacuum that actually preserve those electrons. Basically, at the energy scale, the question is really the matter of energy scale. That at the energy scale, much lower than the Fi parameter, you cannot really have a Coulomb branch in your theory. So we're looking at the Higgs branch. So, and you can also imagine that it's like when you flow down the RGs, that when you go below the scale, below the Fi parameter, then your flux is really confined into those different flux tubes. So this vacuum basically amounts to really picking the NC complex plane in the possible NF flavors, really. And this is usually given by something called Grassmannian. So the crucial thing to know about this vacuum is that as I was alluding, that the gauge symmetry and the flavor symmetry are now basically broken with some subgroup. And crucially, that the gauge symmetry is completely broken. So, so we're basically only taking the kind of simple part of the UNC times the UNF minus. So that's the residual global symmetry we still have. And the point now is that the overall U1 of the gauge group is actually completely broken. And this is actually crucial to actually ensure the existence of topologically stable vortices, which again are going to be labeled by the first homotopy class of this vacuum manifold essentially. So it's like a picking, just like when you doing the electroweak symmetry breaking. Now you have SU2, then you pick the axis, then you have a U1 left over. Then you look at the vacuum manifold. So
excuse me, what is the symbol S in the equation 5?
Oh, this you take out overall trace. So basically now on this one there's a diagonal generator. There's a diagonal generator added, take a trace equal to 0.
You have not broken a flavor symmetry.
I have now completely broken a flavor symmetry.
You have broken any flavor symmetry?
Yeah, I do, because now it's not SUNF anymore. It's really a UNC. They have basically two parts. It's a really subgroup that UNC and the UNF minus NC.
But what does the flavor symmetry breaking here mean?
Well, it just means that some of the quarks also become massive.
Okay. So QCD like constant.
Okay, so right. So what's next? So we have the static solution. Now we want to understand, how the vortexes move. Just like a superconductor, they should move each other. That's why you lose the superconductivity when they start going each other's ways. So you want to really look at the lowest energy, excitation, so to speak, and that corresponds to really kind of moving those vortices around in the transverse direction. But also you can bend its shape. Right? You can bend around its shape in the transverse direction as well. But also there are also those fermionic degree of freedom. So basically you will ask how many those lowest energy excitation, and that boils down to, in physics, that boils down to doing basically a linearized equation of motion calculation around the vortex vector. And that's, to mass, that's basically an index theorem calculation. And that index calculation basically tells you that in this kind of K topological charge vortex configuration coupled to NF flavors, and that would give you a 2K NF, those so-called zero mode, or those lowest energy independent physical lowest energy fluctuation. But there can also be additional fermionic zero-mole fluctuation because you also couple those fermionic degrees of freedom. So, okay, so now we kind of, in our four-dimensional space-time, we introduce a two-dimensional, basically, defects, or basically this vortex in the 3n time direction. And that basically tells you, well, you know, breaking the translational invariant, the Lorentz invariance in the direction that transfers to these vortices. And we also know that because supersymmetry should square to the Lorentz symmetry. So if you break the Lorentz symmetry, you also break some of the supersymmetries. But on the other hand, you can actually preserve, basically, in the kind of along the time in x3 direction, you can still preserve some of the supersymmetry. And in fact, you can actually preserve 4 out of the 8 supercharges in n equals to basically preserve half of it. And this is a very generic feature when you introduce different kind of defect, whether they're monopoles, let's say those instantones, or even domain wall in your theory, that you usually preserve some fraction of a supersymmetry. A very intuitive way of understanding. It's just simply because, you know, they are there, and then they break your Lorentz symmetry, and therefore you expect some supersymmetry to be broken. But on the other hand, now you have some fraction of supersymmetry now get preserved along the volume of the vortices. And what you can do is, if you want to really describe kind of quantum mechanics of those vortex wall volume, and you can those remaining kind of fermionic zero mole and bosonic zero mole actually combine again to form the supermultiplet that transform under those residual supersymmetry. And the theory now describing the vortex wall volume is a two-dimensional 2,2 UK gauge theory that now has some gauge coupling G, but also there are those additional NF fundamental chiros and NF minus NC fundamental chiros. But crucially, there's additional kind of adjoint guy that transform based on the adjoint of the UK gauge. And this guy, you can really try to understand this, like basically the diagonal entry, since adjoint is a matrix. That you basically label where your vortices actually sit in your transverse. And in this two-dimensional theory, that the residual flavor symmetry is basically SUNC times UN minus times NC. Now we have basically the residual symmetry group you have from the 4D. So okay.
Excuse me.
Yes.
So is the size of the vortex one of those?
Right. Okay. So the size of the vortices is actually the size of moduli is basically related to, okay, I didn't write down, there's an FI parameter of this theory.
So once you fix the FI parameter, then all the vortices are of the same size. I'm asking where.
Right. So okay. So there are actually two moduli. Yeah, good. So basically, you are really asked just now. I was trying to ask George. The size of vortices is really given by from 4D perspective. That's given by the 4D gauge coupling times the 4D FI parameter, the inverse. Okay. So how does that encode in this? Well, so one can show, and from beta from divergence, and quickly answer this one. So then the gauge coupling here is actually related to the gauge coupling, which is a separation of NS phi and the default. And that's basically going to give you is related to the FI parameter in 4D. And on the other hand, the FI parameter in 2D, that's related to 4D gauge coupling. So they are also encoded in this theory. Okay.
So in two transparencies, but you presented some singular gauge solution for the vortices.
Right.
So that you can obtain by tuning some.
Right. So this limit is correspond to very good. So this limit is actually correspond to you are setting the size of the 4D vortices to be go to 0, or 1 over e to the v to go to 0. But at the same time, also setting the FI parameter to go to 0, but while keeping the 4-dimensional gauge coupling fixed. That's the limit of going from vortex solution to a surface to a singularity profile like this.
In did something to the gauge coupling.
You did something. You keep the 4D gauge coupling to be fixed. It's actually kind of opposite limit to some of your decoupling. There are other limits like you can decouple the 4D gauge. Okay, so I think let's see how fast I can go in the next 20 slides. So, right. So we are looking at the moduli space. If we are caring about the moduli space of vortex solution, this is actually given by the Higgs branch of this two-dimensional field theory. And now, as we're trying to answer in Kazuo, the two-dimensional Fi parameter is actually related to the 4D gauge coupling by this relation. And if we now actually set the 2D gauge coupling to infinity, or basically setting the 4D Fi parameter to infinity, now the theory basically kind of zoom in to the Coulomb, two-dimensional series zoom into the Coulomb branch. And now we are actually really looking at a n equals 2, 2 sigma model on the Higgs branch. Okay, so we can actually also deform. So just now the 4D theory we talked about are really kind of massless. But we can also break the flavor symmetry in 4D, and by actually introduce some masses like quark masses. So now as a result of that, the 4-dimensional Coulomb branch are generally lifted as well. But they can still be isolated vacuum that exists along those locus. Now it's necessary for the adjoint scalar to also pick out a non-trivial with expectation value, which depends on those complex mass parameter, in order to allow those Q to actually have a non-zero expectation value. So they are basically now this combination of isolated vacuum. And this is precisely, this point is actually kind of interesting in the moduli space. This is actually precisely the point something called a Rudel barrier on the Higgs branch. And why is it really? It's really the point that where your Coulomb branch of the theory actually kind of intersects with your Higgs branch. And what does that do? Well, basically, when you have two branches kind of intersecting each other, that usually means there are additional line degree of freedom that are appearing in your theory to parameterize those flat directions. Or from the Wilsonian effective action sense, that you are accidentally, you are integrating now some of the particle now, which because of some parameter you are changing your theory, that become light, that creates singularity in your partition function. And that's precisely where, this point is precisely where there are additional squawks, to be more precise, actually become massless. Otherwise, at the generic point in the moduli space, because of presence of complex mass parameter, they are just generally massive. So you really only have, you don't have a vacuum anymore. So, and on the other hand, this kind of symmetry breaking pattern in 4D also actually descends down to the two-dimensional vortex wall volume theory. Now, this Higgs branch vacuum in 2D actually also get lifted by those additional potential. Basically, all this chiral scalar field in 2D also pick out additional mass parameter. So they are kind of lifted most of the vacuum, but they still can be isolated, basically minimums that where the vortex solution can actually still exist. Okay, so yeah, I'm trying to kind of find those equations and trying to make a physical sense. So, but furthermore, that in 4D, if you learn any amount of supersymmetry, that you know that the n 4-dimensional n equals 2 supersymmetry, you can also decompose that into n equals 1 supersymmetry, and that's the decomposition. So we can actually also break, something closer to the real world, if you want, that breaking from n equals 2 supersymmetry to n equals 1 supersymmetry, by actually introduce additional superpotential for those adjoint scalar fields that I mentioned earlier. For example, it can be a master, and allow us to kind of integrate it out this way. So basically, you will end up with n equals 1 super QCD, but with additional some adjoints. But then there are some superpotential terms. So what happened to the vortices? Well, when you break a SUSY, generally it's by since it should preserve some